marble? It's going to fall into the bowling ball. And that was the description that Einstein said gravity is. Not a force. What it really is all of space-time curves, and everything in the space-time has to follow that curvature. And then he said one other thing that was really, even he did not like this idea. He's asked the question, what if you take this bowling ball, and instead of it just sitting on the cushion, what if you started to bounce it up and down? Then what happens? Or to the trampoline. You bounce up and down on a trampoline all the time. What happens? Waves, exactly. The same as if you dropped a rock on in a pond. On the surface of the pond, waves would go out. So that is Einstein's picture of gravity. It can wave. It can curve space-time. At the bottoms of black holes, sometimes you've seen those little funnels. It can tear. So Einstein turned our view of the universe upside down by saying space is not empty. It's not an idiot. It does things. And it can curve and it can wave. And what do those waves look like? They look like this. So this was Einstein's picture of space-time that's bent by a massive object. And then if you have a massive object or two of them going around each other, orbiting each other, then the entire space-time itself ripples. So the thing that I'm going to tell you about next is, well, now we know that gravity has a messenger. If these objects, and so here, this is a picture of two neutron stars. And what they're doing is they're orbiting each other. We know, just like the Earth orbits the sun, we know most stars are in binaries where they have two stars that are orbiting each other. But what's special about these neutron stars or black holes is because they have so much gravity, they can give off these gravitational waves strongly enough. And these waves are like any other wave. If you ever learn one property of a wave, it is that if it's a traveling wave, it's that carries away energy. So these waves carry away energy from this pair of objects that's orbiting each other. Where does that energy come from? It actually comes from the orbit. And what that means is that as these objects orbit each other, they get closer and closer and closer together, and eventually they collide. And at the moment of the collision, the space-time goes totally nuts. You get a huge amount of waves. And that's the thing we're looking for. What we're looking for, we set out to do 100 years after Einstein told us these should be there, is to make a measurement of these waves. The problem is that even for very massive black holes not too far away from us, they're really, really weak. So let me tell you about that for a moment. So what these are, so Einstein told us they're ripples of space-time. Einstein did not like them. They popped out of his equations. And, and he was a decent enough mathematician that he trusted his equations. He said, well, maybe the universe actually does this. But there was no real evidence for them. And he actually, in his first paper in 1916, when he first wrote about them, he actually dismissed them. He said, these will be useless. This is what he said. The word he used was a paper in German. And he said, they will never be very useful. All right, then many years later, that was 1916, and in 1970 or so, 1967 to 1970, the first neutron stars were discovered. Now, why was this so exciting? Because in the time of Einstein, we only knew about stars like our own sun. Now, our own sun, even though it's quite massive, it's not very compact. It's 700,000 kilometers. So this was the first time that people said, well, maybe Einstein's gravitational waves could be detectable because they'd be stronger. So the next hero of our story is Kip Thorne. And Kip Thorne was a professor at Caltech. And in late 1960s, 1970s, he made the first calculations to say, well, they're pretty faint, but this is the strength they have. And for those of you who study math, notice that the number is 10 to the power minus 21. So 0 with the decimal point, 20 zeros after that, and then a 1. Okay? Now, the other thing you'll notice is that I've put no dimensions on this. Now, if the science teachers in here would dock you a point if this was the answer to your problem, right? Because you didn't tell, is it meters? Is it seconds? What is it? It's actually really dimensionless. So the strength of these gravitational waves are measured as a change in length per length. So it's a change in length per length. And the way that you can understand that is to ask, well, if a gravitational wave went through me, I'm an object of about 1 meter, so my height would change by 10 to the minus 21 meters as the gravitational wave went through me. Okay? Now let me put a scale on that. Anybody remember what the size of a proton is? Yes, exactly, 10 to the minus 15 meters. So this is 1 million times smaller than a single proton. My height, even now, as I stand here, all of you, they're all objects of order meter for physicists, are changing by a million times smaller than a single proton as the gravitational waves from the universe are going through us. All right. So you would agree that's pretty hard to measure. So then the next hero of our story was this man, Ray Weiss, who was a professor at MIT, and he said, well, wait a minute, maybe they are detectable. And what he said, what his big innovation was, is, look, obviously if you're an object of a meter long, that's too hard. That's you have to measure 10 to the minus 21 meters. But what if you made a really big, long detector? What if you made your detector a kilometer long? Then you only have to measure at the level of 10 to the minus 18 meters, only 1,000 times smaller than a proton, and he showed us a roadmap for how you can do it. So in 1972, he wrote a paper that said, this is how you do it. And then for my own story, I joined his group as a graduate student in 1991, so nearly 20 years later. And at that time, we were setting out to build the first experiments that could actually make this measurement. But in the meantime, Thorne and Weiss, so these two guys, Thorne and Weiss, met, and they began a new field where they started to look for ways to make these detectors. So these are all aerial views of a global network of gravitational wave detectors. And the few things you have to know about them. They all look like they're L-shaped. They're all aerial views because they're all kilometers long. So what these detectors are they're L-shaped detectors. They're usually, in the case of LIGO, which is the US ones on the top left, they're 4 kilometers long, and the measurement is quite simple. You all could do it, just couldn't do it with the precision that's needed. The measurement is as simple as, I want to measure changes in space-time distance. The best meter stick we have for that is the speed of light. So if I had a laser, and I put a mirror at the other end of the room, and I shine the laser at the mirror, the light reflects and comes back to me. If I have a good clock, I measure how long it took for the light to go there and back, and I've measured the distance. Gravitational wave comes through, that measurement should change. That's the principle, and everything else we do, including the 40 years it took to build this, the $1 billion that was spent, is for 2 reasons. The one is you don't have a clock that's good enough, because it's such a precise measurement, and the other reason is that you don't have a mirror that's still enough. So those are the 2 things you have to do. You have to find a way of making the mirrors really still, and you have to find a way of making a good clock. And that's what all of these experiments are about. That's what I've spent most of my career on. And then lo and behold, in 2015, we've made our first measurement of this signal. So look at the time scale. 1972, it was proposed. 1991, I joined, was not me, it's many other people, but my own story is wrapped up in this. And 25 years later, we make our first measurement. What does it look like? So here is a video. These are 2 black holes that are orbiting, and look, these gravitational waves are going out just like ripples on a pond. And what they do is they travel out in the universe, just like when a pond ripple is. It goes out in the universe, and as it goes by, look, it's ever so slightly changing space-time as it moves through the universe. And then it comes eventually to our beautiful planet, and it changes the space-time distance of our planet. Now, this is highly exaggerated. Our planet did not do this. Remember, even in our 4-kilometer-long detector, this will only make a change of 10 to the minus 18 meters. I can't emphasize how ridiculously small that is, okay? So what did that signal look like? It looked like this. So I showed you my most favorite picture in astronomy. It was the first one I started with, Cassiopeia A, the supernova. Since then, this has become my most favorite picture in astronomy. So what you're seeing here is very straightforward. This is the amplitude of the gravitational wave. Look, it kind of looks like a wave. It's kind of noisy and dirty because our detectors aren't perfect. And on the time scale, you see there's 0.2 seconds. So 200 milliseconds. And what we see here was a pair of black holes that were orbiting each other, and they orbited each other for about 1 billion years. And in the last 200 milliseconds before they collided, we picked up the signal. That's what we saw. And you see a few things that are kind of amazing. So look at the vertical scale. The vertical scale is 10 to the minus 21. So that's a huge check mark for Kip Thorne. He told us already in 1967 that the wave should have an amplitude of 10 to the minus 21. Convert that into a length change in our detector,